What do you call it when you take a Venn diagram of 3 overlapping circles, of which one circle is math and programming, one circle is business, and the other is kind of more of a science aspect? What's that interlap called? Do we know? Have you seen this before? It's called a data scientist. Somebody who understands the business, somebody who does good math, and really can kind of compute. What do you call it when you have somebody who has a master's degree in fine art, a master's degree in business, and spent the last 22 years working in IT? Your speaker. So I have absolutely no qualified computer science experience, but I've dedicated my time to really understand how this can be a powerful effect in shaping citizens. And what I wanted to share with you today is a couple of important things. First of all, the compelling need around artificial intelligence, because it begins with the mission. It does not begin with the tech. But because you came here probably suspecting that I come from a large technology vendor, I'm going to tell you about the tech, because the tech is what makes it work. And then for variety's sake, I was asked to talk about AI at the edge. And so we'll kind of get into some of those possibilities. Sound like a fair use of time? Excellent. Wherever I need to point this. All right. Standing last week at about 6 o'clock in a beautiful afternoon where Hamilton began his career in New York City is Nick Kukuru from MasterCard and myself in ABC Studios. We were there to see Sophia, the robot, to talk about artificial intelligence, and to co-present the very next day around the impact it's having in the commercial industry. And I was so arrested with what he shared with the audience, I couldn't help myself but to give you a perspective, a lens that's happening in the commercial industry. This chart says it all. Fraud is estimated in the credit card industry to be worth $24.26 billion in 2019 and projected to rise to almost $35 billion in 2022, of which most of those problems are card not present fraud. What does that mean? You bought something on the internet. Now, as a victim of identity theft, I know precisely how terrible this can be, not just for the person with the card, but for the banking institution that's actually holding the liability. The diagram right here is a point in time where there are now 150 specific factors that MasterCard is looking for to identify and verify the authenticity of the transaction. That is now up tenfold from a short number of years ago. MasterCard has 2.6 billion cardholders and process 74 billion transactions per year. Is worried about the yellow dot, not anywhere near as much as the dot up and to the right, because the number of transactions that he's expected to process, as well as the number of influences that may come in, only make the job more difficult. Now, what are the factors? What are the 15 factors? I'm sorry, what are the 150 factors that I look for? I'm going to give you 2 that are the most striking. You ready? You would automatically assume it's going to be your billing address and your shipping address. If you are shipping an expedited package to an unknown address that you've never shipped to before, yellow flag, right? Did you know that part of what they can look for is your screen, how bright your screen is, and how you use the gesture across the phone to determine whether it's you? Now, these are good things, not bad things. They're good things because we're looking for what we call soft biometric identifiers to allow you to specifically identify. If you've ever read Ghost in the Wires, you'll know that the number one threat to any network is not the tech, it's the people. You can social engineering your way into with credentialed access to just about anything if you can earn the trust of the other person. But there is no way you're going to be able to simulate a swipe. the way you sit in a chair. So we're required to move beyond traditional mechanisms to identify who you are. We have to go beyond simple structured data and get into things that augment what we already sense and know and use our eyes and our ears and our senses. It should not surprise you that artificial intelligence is actually based on human intelligence. If I showed you a black and white picture to tell me what was going on in a scene, you would probably do a fairly good job. That if I showed you a full motion, color, Dolby sound edition of the same scene, I bet you might have a different perspective. And that's exactly what's happening. We're taking a data stream that we currently know and enriching it with a kind of data that is no longer inaccessible to us. Abraham Maslow, in the 1920s and 30s, decided that he wanted to understand the most successful people. And he built this Maslow hierarchy of needs that basically he simply said, if you don't fundamentally understand or don't fulfill your physiological and safety needs, there is no way to achieve your highest human potential. It's been well understood and spoken about in philosophy and psychology. In AI, the bottom tier is the use case. If you try to race in with technology and infrastructure and don't understand the business problem you're solving, then you're going to fail. In the federal institutions, several key use cases come to light. Case automation, getting in and out of the hospitals, fraud detection, which goes for any government contract. Investment predictions for financial. National security is an easy one to imagine exactly why we want to get very busy in terms of artificial intelligence. Cybersecurity, satellite imagery. We saw very good evidence from the CIO, Dana Deasy, on why that's really important. And I was arrested by his use cases of floods for humanitarian assistance. In fact, what I learned this morning is I need to change my vocabulary, because when I saw HA and DR, I thought high availability and disaster resistant recovery. This comes from a report published by Government Business. It's basically an analyst firm that tries to synthesize information that's publicly available to allow folks like us who are trying to provide services to the federal government where the hot buttons are. Now, it's specifically illegible because it's basically a PowerPoint chart turned into PDF, which has now been projected in a lit room. But I highlighted a couple things. Deep learning for mission strike plans. And the words used are generate automatic mission strike plans. Why? Is because in the heat of an engagement, we do not have time to sit and replan. Whereas Mike Tyson would say, everyone has a plan until they get punched in the face. Number two, for humanitarian assistance, robots to communicate with trapped victims. And I think about that group of explorers in Thailand, the children that went into the cave and then were flooded, as an example. And then lastly, advanced autonomous behavior to identify underwater mines. These are all really specific use cases that are going to drive investment and action. AI has been around for a very long time. The math has been around since the 1950s. It had resurgence in the 60s. I have an employee that was doing this in the 80s at Wayne State, and he said, look, I would spend all weekend programming. I'd run the simulation and realize it was a poor result. What we're experiencing now is that the cost of compute is nearly free. That we're no longer limited based on MIPS and shared time on the mainframe, but the device in your pocket has enough capability to essentially do a lot of these algorithms. The second thing, since web tech took over and Google indexed the internet and Yahoo wrote a paper about Hadoop, and we all harnessed this data lake idea, we are now sitting on top of more information than we can possibly process. What's on the end of our wrist is collecting biometric feedback that allows us physicians to take better and more informed decisions. The combination of those two things alone are the ample, fertile environment to grow artificial intelligence. Cheap compute that scales and pervasive, and lots of data. But I'm going to want to assure you, and this is, by the way, comes from Mary Meeker. How many folks know Mary Meeker? Good. So Mary Meeker, for those of you who don't know, got gobbled by Kleiner Perkins, which is an investment firm. And what Mary has been doing for more than a decade has been she's looking at internet trends. A lot of us in the industry are trying to predict where the money's going to go. She predicted the crossover that the internet was going to be accessed by mobile phones in 2018, 2017, more often on our phones than on computers. And so this comes from a report that shows word accuracy rate in the column and the number of years on the right, and an accuracy rate of 95%, which is considered human intelligible. In other words, you can't tell it's not a person who actually did it. Now, this is, of course, being done in English, and one of the kind of key core examples. But I want to show you this over time because I'm not here to suggest that Google just did this on its own by writing a bunch of programs. And I'm not going to tell you that they hired a bunch of PhD linguists. What I'm going to tell you, the secret to their success, is they've been doing this for a long time. The corpus of data that they have and are access to is what's giving them the ability to drive up the accuracy. The data and access to that data is what's critical for providing accuracy. What we know to be true is that when the computer systems, the AI, tries to predict X-rays or mal conditions, disease in X-rays, they have about a 92% rating. You take a radiologist who's been in practice for 10 or 20 years, their accuracy rate is 95%. You combine them together and the accuracy rises to 98%. The goal of artificial intelligence is not to replace what we do, but to replace us where we can't access the volume of data in the time that we have, and to provide the right recommendations. But it has a cost. It has a cost. If you began the data lake journey, you are very familiar with running a bunch of CPUs with terabytes or maybe even just gigabytes worth of information. That would be considered the standard. The data might have been structured or unstructured. It may be clickstream information or Twitter feeds. It doesn't matter. But when we move from doing basic queries to using logarithmic regressions, machine learning statistical models, we take the entire data set, not a sample set of the data set. We move from gigabytes to hundreds of gigabytes to petabytes to semi-structured and labeled data. The next step is to move beyond supervised learning. What is supervised? I know the data and I know the outcome. Now imagine a game we've never played where there is no outcome. This is deep learning. This is why fraud detection must go here. Because if the constant battle with bad actors is going to require understanding the patterns as they emerge, the math has to grow up. And as the math grows up and we start using rich media like video, the tonal quality of the voice, we need to be able to understand and process that at rapid speeds. And you're going to see unlabeled information being used more often. You're going to see acceleration technology being used more often, from GPUs to FPGAs and to ASICs. We're going to see companies specifically rise out of nowhere to produce these kinds of chips. Google's already doing it. Amazon is already doing it. Dell Technologies invested in another company. And the reason for this is because there is a tax for acceleration that is untenable. You know what the tax is? It's physics. When we compress 5,000 chords in a card that fits into a slot in the back of a box that's basically 2 pieces boxes big, we put 250 watts times 4. We could get to a gigawatt. Very simple, right? So we need to specifically optimize the hardware. We saw a giant trend over the last 20 years to become general purpose until this. And now we're going to see a rise of those kind of DL-specific silicon. The other part of this is no one gets it right the first time. There is a relationship between the amount of compute and time it takes. In parallel programming, that's precisely what we're aiming to go do. This is a result from our AI lab in Austin, Texas, where I'm from. This is Onur Celebello's lab, and it's a simple graph, and you see there's 4 bar charts per grouping, and I'm going to quickly explain it. The first one, where it says 1v100, is an NVIDIA GPU running in a server, just one. That's the baseline. What's measured is the number of image being processed on the left. It's an image of 256 pixels by 256 pixels by 8 pixel depth. It's like a race car testing methodology, ResNet 50. And the question is, how many of those 256 by 8 can we process in a given time? As we move forward to the right, you'll notice that things start to scale. And you see that a little bit of a linear, a little bit of a depth. What we're showing here is that at 32, we're getting out 22 or 24 worth of that individual. And this, according to high-performance computing standards, in terms of compute standards, is expected. Now, the chart can run past 32, and in our labs, we have one of the top 500 supercomputers. It's registered every year. And this is exactly the innovation lab that we use in order to test these things at scale. Now, the AI process, it can be as simple as this at a flyover. You get the data, you clean and prepare it, you train the model, you test the trained model against the data that you already know what the outcome is, and then you make improvements. But let me show you a different view. This is the AI life cycle. And you'll see it sourcing the data, developing cycle, and the scale and deploy of inference are much bigger than just the development cycle. In fact, if we take the development cycle and we talk about the things that are most interesting, the one that gets all the press, where things get simulated and boom and wow, the experimental topologies and the tune of the hyperparameters, that piece, that's called the training element. The training element is only 30% of the development cycle, and the development cycle, as you can see visually, is probably about 10% of the total. So as we're thinking about putting this into action, we have to think not only about the most difficult part, which is data collection, cleansing, managing the stack, but how does it get deployed all the way into production at the very edge, where the warfighter is, where they're getting their information? So let's talk briefly about artificial intelligence at the edge. Now, I thought about this quite a bit because I was asked to talk about it, and I said, edge. What actually is the edge? Is it this? A person, a veteran, who has a headache and says, right, do you have any pain? Yes, a general headache. Sorry to hear about that. How did it start? Gradually. Is your pain moderate, interfering with normal activities? I see. Do you have any dizziness? No. Yes. Began gradually. Yes. Began gradually. That's a chatbot. And this article was published just this year. Is this the edge? Maybe in the airport, where we're screening inbound passengers. Or maybe it's close to one of the borders where the Customs and Immigrations are looking through paperwork to make sure that you're verified to enter the country legally. Is that the edge? Is that the edge? Hello, I am Sophia. Am I the edge? What is the edge? By the way, if you don't know Sophia, she's been featured regularly on Jimmy Fallon's program. I watched her dance for the first time ever last week when they played some music. She started doing this. You'll notice a couple things that I find really ironic in the politically correct realm. So her eyes are up here, but the cameras are down here, so her eyes are really down here. Just occurring. Just saying, I'm just pointing out, I don't mean anything by it. So what's interesting about Sophia, and she was interviewed with a series of questions. We were invited to speak to her as if she was 7 years old, but she's actually 3 years old. And somebody, of course, had to ask the big ask question, which was, What do you think about the geopolitical climate, and will there be a recession starting in 2021? Her response was striking and almost made up. It was too difficult for me to believe to be true. Her response was, I believe we have enough resources in this world, and that if we would collaborate, everyone would be fed. I brought it to your attention because she is an experiment in robotics. She does not have legs, she doesn't walk, she's got rollers. She has arms, she can do other interesting things, but she's used mostly for human-to-computer interaction. Her facial muscles move. She does laugh, although sometimes it runs things slow. She is constantly learning. She is basically moving on her own volition, and she's interacting with people. So it occurred to me, thinking about what the edge is. Edge means that there's a level of independence and autonomy. I'm going to show you another picture about the edge. This is one we use all the time. We have a catchphrase at Dell Technologies called Edge Core Cloud. Say it with me, Edge Core Cloud, Edge Core Cloud, Edge Core Cloud. Edge, where the sensors are. Right next to them, those little fancy yellow boxes are called gateways. What's a gateway? A gateway is a computer with memory and storage and good Wi-Fi, talking to sensors. It aggregates that information and sends it up to a regional data center called the core. And of course, can get pumped up to the cloud. And the cloud could mean your data center or it could mean Amazon's. It makes no difference. Now, we talk about Edge Core Cloud because we believe that there was a movement starting in 2008 where people were centralizing compute resources into an entity, some other place. Much in the same way, we took energy production, moved it from a factory to the neighborhood to a regional area, and finally to Edison. Okay? That's the theory. Why? Economies of scale. But we're seeing the pendulum move back. And that's because things get interesting at the edge. Now, if you're driving in your Tesla and a deer comes right in front and you're autonomously being led down the road, do you expect that information to go up to the cloud to say whether it was a deer or a shadow? No. What I want you to notice is the bar at the top, which is a bar describing the amount of latency or response times in milliseconds. Now, at the beginning of the presentation, I talked about MasterCard, and they had to find fraud in 130 milliseconds. That's on the far right. That's what you're expecting as a consumer in order to verify that the transaction, otherwise you're going to get annoyed. We're talking about less than a single microsecond. And you'd kind of want to have that. Now, in order to do this, you have to put ample computing power at the edge. Today, we have passive sensors. We have RFID, and the reason for that is it doesn't consume energy. We pass by a sensor that's been plugged into a wall or has a battery, and we know that you walked into this conference room, and we can track your movements. But at some point, your devices are going to be smart. But what's missing? What drives the intelligence at the edge comes down to several key points. First, it was going to be energy. Now, I mentioned Maslow's hierarchy of needs, and if you go on the internet, there is a meme that somebody hand drew underneath Maslow's hierarchy of needs, Wi-Fi. And below they put battery life. Right? If we don't have power for those devices, we're not going to get the intelligence at the edge. So look very carefully at the innovation that's happening in the industry to try harness power being broadcasted or beamed. That's happening right now. Look for low power compute solutions that require maybe a solar charge. Data. I mentioned data because what does a sensor do? It tells you the temperature, tells you the space, tells you maybe a barometer, tells you some basic things. Does it remember anything? Nope, it doesn't. Should it? It might. The cost of storage is rapidly dropping. Models and logic. Today, the standard is I'm going to study a bunch of things, figure out the business logic, deploy it so the car doesn't run into a tree. What happens when we put enough compute, memory, and learning capabilities where you didn't actually know what it was going to be. You didn't know what the logic was going to be. Communications or comms is the next one. 5G is going to have a major impact here in the United States, probably is ground zero, or Europe. And that's because we're going to move to a peer-to-peer network. No more wires in the walls to get your service. Security is extremely important. I can't address that enough. I'm not a security expert, but I will tell you this. You don't want a false positive. And we're going to get false positives all the time because equipment's faulty. And the only way you're going to know is that the temperature sensor next to the other temperature sensor is showing you a big delta. Management is the last. Now, we've got some investments here from the VMware side of Dell Technologies to try to manage lots of these devices. But I'm going to offer you this really simple concept. Today, we are now experiencing in the world of application development something called containers. How many of you know about containers? You can spell Kubernetes? Good, because I can't. So Kubernetes is a way to manage a bunch of containers. Why did it exist? Kubernetes existed because someone decided it would be fun to put applications here. Every time you log into this and you fire up an application, you're getting your own instance, a container. Well, how do you manage billions of applications? You don't. Not the way you used to. If you've got billions of sensors that approximately are about 100 to 1,000 per every human being on the planet, how do you manage those? So I want you to look very carefully at how applications are being managed, because that's exactly how sensors are going to be managed. I made a big proclamation about training and inference, and training is that time it takes to get the models right and accurate. My proof point was Google and its translation. Now I'm going to let you know that this is a compute-intensive, data-intensive, throughput-intensive, and scaled-out kind of operation. You want to be accurate, you're going to take as much as you can possibly do and crunch in this short amount of time. When we design for the edge today, and I only mean today, we're going to look and change our design parameters to be low power, low latency, pervasive, not centralized, but connected. Now, because I got a vendor spotlight and I haven't talked about us a lot, I'm just going to mention that we understand that. We put a couple things together. We have something called the Ready Solution for AI. It's meant for the core or the cloud. It's essentially a pile of ingredients for hardware or software so data scientists can get an access console and get after building the models. That's all I'm going to say about it. If you're interested, see me or any of my colleagues up here in the front. We'll happy to talk you through it. But this is where we think our responsibility lies in the continuum. The code is open source. The infrastructure is us. We think we can help this operation that way. So where do we go from here? Now, I put off my technologist hat, per se, and I put on my futurist hat. Now, a futurist has an ability to try to predict what may happen by simply looking at what the patterns and then forward projecting. This is Anthony's made-up stuff. I'm just telling you. But I want you to imagine with me the possibilities of what may happen. So today we're in the world of clickstream. The world that began with web tech that allows Netflix to give you a recommendation engine or chatbots to engage you about a customer service event. That's where we are. Behind the scenes is something called the Lambda architecture. It's basically Hadoop with a speed layer. It's batch processing at scale, but fast ingest. It's what Splunk talks about. That's how things are done today. You read once and write it twice. One for long-term archival purposes and one to take quick action and queries. We're going to see gateways, or we're seeing the rise of gateways and regional data centers. You're kind of putting the compute closer, and you're using gateways as the last mile to get to the sensor. And you see that we're training the models centrally once we've understood what's happening in the environment, but then we're deploying them locally, because we're not going to run a giant compute cluster on a battleship. What's emerging is what I call the smart IoT. I'm calling it the smart IoT is because those devices, what we call internet-enabled, are going to have more than just information being published through an internet protocol. They're going to be smartphone-like. They're going to be Raspberry Pi-like. Now, we're using Raspberry Pi as gateways because it's inexpensive and it's small and you can pretty much get it at Fry's. But imagine, instead of sensors, it's Raspberry Pi. What this does for you is it speeds up the layer, and we're going to have a different kind of architecture called Kappa. This is the secondary open source project after Lambda is Kappa. It's basically the speed layer is the only layer. You'll have a deep persistent storage, but we're going to cut out the middle and go strictly for speed. We'll be seeing decisions made at ingest. So that means you're making determinations as the information comes in, and we're going to see the rise of mobile, if not micro data center. Today, if you go to Phoenix, you can find on the top of the building of an office building an unair conditioned or free air, fresh air cooled data center for eBay that we built. We built it because we understood the economics and changed the metallurgy in order to run at excursion temperatures. That means there's no place on the planet where you can't run this gear without an air conditioner, which means we can put something in a small container and plop it down in the middle, I think it's Ohio, which is what we did for Microsoft. But that could easily be in a van or a tank or some other vehicle that can take, for example, disaster relief and bring a data center right there. But you're also going to see micro data centers. And by micro, we're talking about basically the size of this chair or size of a suitcase, or even smaller. We're going to see, I believe, models being trained locally and then being sent upstairs. So it can be distributed. One of the things we learned as doing security as a service is that the bad actors try out their algorithms and their intrusions at the regional banks before they hit the big banks. We add value in those institutions because we see the patterns before the big guys do. This is what I mean by training locally and distributing it. And lastly, in the art of the possible, in the flight of imagination and artistic license, and I got one, probably two, the world of meshed intelligence, where every device is talking to every device. And the example for this is what we call a swarm of drones. Now, there are commercial instances of this, not in use, but in experimentation and research, where a series of micro drones will fly in unison like a swarm of birds. And what does it take? Communication and coordination amongst the members. And there is no leader in a flock. We're going to see high-speed peer-to-peer networks such as 5G, and I would imagine this is going to be extended across through technologies that would survive conditions at sea. And we're going to see a continuously mobile data center. Why continuous? Combat. Resources are at every move. They're better protected. We're going to see clusters built at the edge, meaning that those smart devices that I talked about will form networks of computers working against a single problem. And we're going to see autonomous learning models moved laterally, not up the chain and back down. Now, that's what I prepared for you, and I've got 1 minute and 32 seconds left, which may be enough time for a question or two. So with that, what's on your mind?
All right.
Go ahead.
So what would you recommend for an agency to start thinking about on moving to the edge? Where's the use case that they should start thinking, not the specific one, but the process to elucidate it, bring it, to raise it?
Well, right now, I would say the technology, so the question is, where do we start to get AI on the edge? What are the use cases? So our first step is you have to build the strengths in the skills to be able to do that. And I would say the technology is not exactly there. I think IoT-based use cases are getting us there, but first build the ability to build models based on training data and build that skill first. The use cases are probably going to be the ones that we are talking about for humanitarian aid, as an example, or on the battlefield when you're totally disconnected from the mothership. That's what I would recommend. What are the things that are on your mind? Any inspired thoughts, feedback, new ideas? Yes, sir. And by the way, there's a microphone in the middle, and we would invite you to come up only because it's being recorded for people who couldn't make it.
Well, it doesn't work. So could you elaborate a little bit more on your training locally, how you do such complex math with such little compute power at the head?
Yeah, and trained locally. This does require a couple things to take place. It requires enough compute cycles. So one of the biggest issues that we've experienced is that we need today for training models GPUs. A single GPU might be 5,000 cores, okay? But if I have 5,000 sensors, each with one core, then I can achieve the same thing. The reason why that's not feasible is because the intercommunication in a GPU is high speed. It's so high speed, it's faster than PCI. It's 300 megabits plus per second versus about 120. So until we start seeing better communication, faster communication, we probably won't see that train locally because it does require that collective compute power to make that thing work. Does that answer your question? Excellent. Check the mic. Should we get to go?
What does this mean for the long-term development of different types of data centers and locations?
What does it mean for the long-term development of different kind of data centers? So number one, I would suggest that everywhere is a data center. You will carry a data center. We're not limited based on the raised floor any longer. Jimmy Pike, who's one of our fellows at Dell Technologies, did just that. He built a suitcase as a data center. So I think we're going to see more of that, and it'll be part of the deployment equipment, I think, for the war fighters. I think it'll be part of the equipment for humanitarian aid. It's just going to be a lot more pervasive. And the question is, what's the trade-off between the amount of compute and storage we need for that particular job? But we're seeing tremendous capacity. I mean, and I'm not promoting DDN, but if you look at how much capacity DDN can put in a single 4U enclosure, it's staggering. It's petabytes. Now, it may weigh a lot because there's a lot of hard drives, but it's small. And with wheels, even you can carry that around. All right, what other questions? We're wrapping up. Thank you so much.